Welcome folks to lecture 4. Now lecture 4 is very exciting lecture because we discuss the current sources and current mirror sources. Basically, inside the CMOS analog circuit, how can we bias our amplifiers, bias our circuits or our amplifiers using current sources. In this particular lecture, we're going to talk about how we create current sources and how we implement them inside the IC chip, which is very exciting and unique way of looking at it. In order for us to do that, let's go back and do some basics and then show you how we're going to develop the actual real circuit that is implemented inside the IC chip. So let's assume we have a circuit, and for this circuit we would like to bias it using a DC current source, and the value for this current source is I0. We can implement this current source using a transistor. So the circuit is connected to a transistor. This transistor is called M1, and we will bias the transistor such that the current I0 flow through that transistor. So what we did so far is we implemented the current source using a transistor M1 here, and if we bias the voltage at the gate of M1, we can control the current that is flowing through that transistor. So that's how we implement the current source. The current through the transistor may be controlled using biasing voltage. For example, biasing the differential pair transistor in the differential amplifier. Remember, in the differential amplifier we said we have transistors M1 and M2 connected to the current source, and the current through that current source is ISS. Now if we would like to implement current source, what we do is we replace this current source with a transistor. We're going to call it M3, and we will bias that transistor at V bias such that the current flowing through this transistor is ISS. That's how we implement the current source. The question now is that, how can we create bias? I know that if I have the right V bias, I will have the right voltage ISS. Now the question is, how would I create V bias? The answer is very simple. This is the V bias circuit. The V bias circuit says that we're going to have VD connected to a current source. We're going to call it IREF, and this current source is connected to a diode connected transistor called M1. If I adjust the value of I reference, I will be able to create a V bias at the gate of M1. So the question now is, how can I create I reference? Remember, this circuit is about V bias. How to create V bias? That's what we're doing here. Well, to replace this current source, what I do is I add a resistor called R reference. So what I have now is a voltage source connected to R reference that is connected to a diode connected transistor. And now if I control the value of the resistor, I will be able to control the current going through the transistor. Then I will be able to control V bias. You see, let's say it one more time. I would like to change the value of the resistor to change the current I reference such that I get the voltage I want V bias. Then the overall current source will look like this. I have VDD connected to I reference, which is connected to the diode connected transistor, which give me V bias. Now V bias is connected to the current source, which is M2, and that is connected to the circuit. You see that? And remember, we said that this current source is replaced with a resistor. So now what I have is VDD connected to a resistor that is connected to a diode connected transistor that will create V bias for me and V bias controls the current source transistor M2, and that will give me the right current I out. That biases the circuit. We call this circuit the current mirror. Why we call it the current mirror? Because these two transistors, they are a reflection of each other, so they are almost like the mirror image of each other, right? Basically, I out is the mirror image of I reference, and note that the voltage VGS1 is the same as VGS2. Now we are interested in the mathematical relationship for the current source. Basically, how can we find a mathematical expression that defines the current through the bias and circuit, which we call I.O. Keep in mind that what we have here is I reference that goes through the transistor M1, which will create VGS across this transistor, but same VGS across M1 is across M2. So these two transistors have the same voltage across them, so they behave as current mirrors. They are a reflection of each other, and this way we will be able to define the value for the current through M2. So the first note, we would say that I.O. is the mirror image of I reference. That is because VGS1 is equal to VGS2. Then we can find the expression for the reference current IREF to equal to 1/2 mu n COX W over L1 times VGS1 minus V threshold quantity squared times 1 plus lambda times VDS1. So this is the current equation for the transistor in the saturation region. The transistor is in saturation because it is diode connected. We know that the diode connected MOS transistor always operates in the saturation region. Then we can also say that the output current I.O. will equal to 1/2 times mu n COX times W over L2 times VGS2 minus the threshold voltage VTH quantity squared times 1 plus lambda times VDS2. What we're going to do next is we would like to find the ratio I out over I reference, which is nothing but 1/2 mu n COX W over L2 times VGS2 minus V threshold voltage quantity squared times 1 plus lambda times VDS2. This is I out divided by the IREF term, which is 1/2 mu n COX times W over L1 times VGS1 minus V threshold voltage quantity squared times 1 plus lambda times VDS1. Now, what we know is the following. We know that VGS1 equals to VGS2, and since this is in the same wafer, which uses the same process, that means the threshold voltage for both transistors is the same, then we can cancel VGS2 minus V threshold voltage quantity squared with the VGS1 minus V threshold voltage quantity squared. And also the 1/2 mu n COX for both transistors are the same, so they cancel out. Then the ratio I out over I reference will equal to W over L2 times 1 plus lambda times VDS2 over W over L1 times 1 plus lambda times VDS1. This equation is very powerful. Why? Because now I can tell you that what is the current reflection between the two transistors. The current through M1, which is IREF, can be reflected to M2, which is the bias and current. Basically what I have to do is select the right W over L ratios. Usually this term, 1 plus lambda VDS term, is very small that it can be neglected for approximation. when you do the biasing for M2, make sure M2 is in the saturation, which means that you're going to have a restriction on the common mode voltages of the differential amplifiers, right? Because remember, the current source is used to bias differential amplifiers, so make sure that the transistor M2 is in saturation, which means that the common mode voltages of the differential amplifiers are not low to force this transistor to go into triode. It's another design criteria that you have to look out for when you go through the design of the operational amplifier. And when you do the biasing for the differential amplifier using a current source, make sure that M2 will be in saturation. By any means, if we assumed that lambda is much less than 1 and VDS1 is approximately equal to VDS2, then we can say that IO over IRF will equal to W over L2 times W over L1, or we can say that I out will equal to W over L2 over W over L1 times I reference. And that's the beauty of the circuit. Basically what you do is you say that I will be able to design the W over L ratio of the transistor, so the geometric structure of the transistor, the size of the transistor, determines how much current will go through that biasing circuit, determines the current of the current source. And this is very powerful. This is very practical circuit we have to learn, and this very useful circuit that we actually use it when we develop analog IC circuits. Very fundamental, but it is used. Why we have to learn the circuit? Well, when we implement the current source, we said that we implement this current source using a resistor. So we have used the resistor to implement the current source, and this resistor takes a large area. But why are we using the resistor, or why are we using this circuit to implement the biasing? The reason is one current circuit biases multiple circuits. For example, let's say that we have circuit 1, circuit 2, circuit 3 as shown here, where each circuit will have a biasing current I1, I2, and I3. Then what we can do is we can have a transistor for each current. So we're going to have M1, M2, and M3 to bias these circuits, where all these transistors are connected into one reference circuit. So what we will have here is the reference current source connected to the transistor reference MR. And I can adjust the values of I1, I2, and I3 by adjusting the W over L ratios between the reference transistor and the biasing transistors M1, M2, and M3. So you can bias multiple circuits using one reference circuit, and that is the reason that this circuit is powerful. Also, it is possible to steer the current, so the biasing current I/O will flow from the PMOS transistors. What do we mean? Let's assume that you have the circuit. That's the biasing circuit. You're trying to send the current I/O through the circuit, but you're going to send it from the top to the bottom. Basically, you are trying to bias an NMOS transistor, not a PMOS transistor. So you're trying to bias the current from the top, right? And that circuit becomes handy in many situations. We will discuss them later on. So what you do is you say that I will have the bias on transistor M4 to inject the current I/O into the circuit. So that means I'm interested in biasing the voltage for gate M4 to bias the circuit. Now the way I will do that is I will have my reference circuit as shown here. That's the typical circuit I have, right? And then this circuit will give me V bias to bias transistor M2 as shown. So now all what I did is I used that classical configuration to bias M2. Now there is current going through M2. This current that goes through M2 will also go through this transistor M3. And if I connect M3 in a diode connection, then I implemented a reference current source that will determine the voltage VG4, which biases a transistor M4. So that's the way the circuit works, and it's very useful because sometimes you are interested in biasing the current from the top. And you can steer the current. The current can be biased to be pulled down from the bottom of the circuit, or you can steer it to bias the circuit from the top. and that's how you steer the current. So this is how you steer the current source. We can also use cascaded current sources to make them independent of VDS. So let's show you how we can do that. Here's our reference circuit where we have the reference current connected to M1, which biases M2. Now what I'm going to do is I'm going to cascade M2 with M3 with another V bias. So now I have VB coming through this M3. What's interesting here is that the current IO is the same current flowing through M2 and M3. But what I need to do is I need to find another value for VB. So I need another bias and voltage for VB. So the way I'm going to do that is I will also connect another diode connected to the transistor to bias the voltage VB. So the way the circuit will look like is I will have the reference current as shown here, which is connected to a diode connected to the transistor M4, which is cascaded with M1. And M1 and M4 will create the bias voltages VB and V bias, and they will bias transistors M2 and M3 and make IO to flow through the circuit as needed. This particular circuit will make the current to be independent of VDS. The current does not depend on VDS. There are several other topologies that can be used to use the current source, but the idea is the same. Is you're gonna bias one transistor which gives you the voltage at the gate, and then you reflect that voltage at the gate to the other transistor, and the W/L ratio between the two transistors tell you what's the ratio of the reference current to the biasing current. That's the idea of the current source. Very practical circuit, yet very simple, and it is widely used in analog IC designs. The current source can be used as active load. Remember, load means it's a resistor and active means transistors behave as resistors. So the current mirror source can be used as active load, which means a resistor, right? So basically the current mirror source acts as an active load. We will build this idea of implementing the mirror current source as an active load to the desired circuit, to the circuit that we are really interested in two steps. So to do that, let's go back and look at the PMOS version of the current mirror source. So the PMOS version of the current mirror source says that we will bias the circuit from the top. So we have I reference connected to a transistor, for example M3, that this transistor M3 is diode connected, where this M3 determine the bias and voltage for M4, and then that will give you the current IO. This current source may be used as active load in the differential amplifier. So let's show you how we can do that. Remember that the differential amplifier says that I will have M1 and M2 biased by a current source, and here is the input voltage Vn, which is the differential input voltage. Now these two transistors will give you an amplification at the output. So what we will do is we will say that the load at M2, whereas in this case will be single output differential amplifier, will be implemented as a current source. So the load at M2 is implemented as the current source, which is I reference connected to M3 and that connected to M4, while the output of M1 is connected all the way to VDD. Basically, the current source is a load at the output. That's basically what we did. And now we are interested to find the gain. The gain can be expressed as the voltage gain AV will equal to capital GM times RO, and capital GM is the transconductance of the amplifier, and RO is the output resistance of the amplifier, looking at it from the output. Then we can define that GM, which is the transconductance of the amplifier, to be IO over Vn. Keep in mind that this is all AC signal here, so the output AC current over the input AC voltage is the transconductance, and we know that for this particular transistor the output AC current is basically will be GM1 times Vn over 2. Remember that GM1 and GM2 is the same, and then we're gonna divide by Vn, so you can see that the Vn cancels out, and that basically will be GM1 over 2. Remember, the AC current through the transistor M2 is given by Gm times Vn over 2. We are assuming here half the voltages are applied to both input transistors. And that's very interesting. What it says is the transconductance of the overall amplifier is basically 1/2 the transconductance of the transistor. So now what we are interested in is solving for RO. To solve for RO, we apply Thevenin theorem at the load of the AC circuit. Then the current source is replaced by RO4, because looking back into the transistor of M4, we will only see RO4. And M1 is replaced by 1 over Gm, and M2 is replaced by RO2. And that makes sense because when you look up into M4, looking into the drain, so you're going to see RO4. When you look down into the drain of M2, you're going to have RO2 in series with looking into the source of M1, which is nothing but 1 over Gm R1. So when we do that, we can see that RO equal to 1 plus Gm2 times RO2 times 1 over Gm1 plus RO2 in parallel with RO4. So the way we did this is basically by the analysis, and the output resistance RO approximately equal to 2 RO2 in parallel with RO4. Then the gain is given as AV will equal to Gm times RO, which equals to Gm1 over 2 times 2 times RO2 in parallel with RO4. The way we solved for RO is by applying a test voltage and a test current. We skipped the steps here. You can easily verify it when you use the small signal equivalent circuit, and you will be able to get the same answer. The problem with the circuit is the current through M1 is going to waste, right? Because half of ISS will go through M1 and is going to waste, and in addition, I'm using iReference to bias M4. The solution to this problem, to use the current through M1 to bias the current going through M4. So instead of using another reference circuit that biases M4, we're going to use the current through M1 to bias M3, then bias M4. So the circuit will look like this. Here is the differential transistors M1 and M2, which are biased through ISS, and they have Vn. Now when we go to the load, here is M4, but M4 is biased using M3, and M3 has the same current as M1. See, and this is a little bit clever because now we do not waste the current going through M1. We have to make sure that M3 is a mirror of M4 because you want to make sure that the circuit is as symmetric as possible. Then always I3 equals to I4, right? This is the requirement we have to have. Otherwise the circuit will deviate and you will have some problems, right? Because the current ISS must be split in half between M1 and M2, and then the currents through M3 and M4 should be equal. Then we have to say that M3 and M4 are mirror images of each other. Let us have more notes on the single-ended differential amplifier with active load. This is basically the circuit we are discussing. The circuit is extremely important. You should understand the circuit. It's very fundamental and basic circuit. The first thing we have to see is that the transistors are symmetric. Why the transistors are symmetric? Because remember that the bottom transistor M1 and M2 are differential amplifier transistors, which means that the same DC current has to go through both of them such that GM1 and GM2 is the same. The same AC current flowing from M1 will flow through M2, right? So this is by symmetry of the differential amplifier. This symmetry is required for the differential amplifier. Then we can always say W over L1 equals to W over L2. Why is that? Because VGS1 is the same as VGS2 under DC biasing conditions, and the same threshold voltage applies. And if we neglect lambda, then the only thing remains is W over L1 and W over L2 to fulfill the requirement of the current equality. W over L1 should equal to W over L2, right? Then the current through M1 and M2 are equal, which is the same current going through M3 and M4. You see that? This is very important. Then, by doing so, what we see now is VGS3 is the same as VGS4, and it is the same IC wafer. That means they have the same process. The only way we can equate I3 and I4 is by making W over L3 equals to W over L4. So basically the circuit is symmetric. The size of M1 is the same as the size of M2, and the size of M3 is the same as the size of M4. Believe it or not, the size of the transistor determines the design criteria almost for most analog circuits. That's why people like CMOS technology, because all what you have to do is just to scale the size of the transistors, and then you are ready to fabricate the IC chip. Of course, there is more stories than that, but the basic concept is scale the transistor size and you should get the behavior you want, or you can alternate the behavior of the circuit. Also, all transistors must be in the saturation region. They must be in the saturation region, otherwise that's something we know. Whenever any of these transistors depart the saturation region, it's not an amplifier anymore. This circuit is important, as I said. The reason it is important is that the number of transistors is minimal. The number of transistors is minimal while you still sustain a large gain. This circuit is single-ended output circuit, which means that you cannot use it for differential output amplifier. Remember, we discussed that the differential amplifier can have single-ended output or differential output. This is a single-ended output, so there is applications where this circuit cannot be used. Serializer, deserializer circuit is a classical example where a single-ended voltage cannot be used. However, the op-amp is a classical example where this circuit can be used. This circuit has lower gain than the differential output differential amplifier, but still gives you a high gain, but it is lower than the differential output differential amplifier. In the differential output differential amplifier, you will use external circuit to bias the top transistors. Over here, we don't. We used one transistor to bias one because we are interested in the output to be single-ended, which means we are only interested in M4, so M3 here is used for biasing. Now let us discuss the large signal analysis. Basically, we are saying that if we swing the input voltages by large values, what happens to the circuit? So we are interested in the first case now. If Vn is bigger than twice the threshold voltage, that means we have enough voltage to turn one transistor on or off without the effect of the bias and current ISS. Under this condition, if Vn is bigger than twice the threshold voltage, then the input voltage is large enough such that M1 is on and M2 is off. If M2 is off, then I2 will equal to I4 because they are the same current flowing through them, and they will equal to 0. Now what's interesting here is I4 is 0. but VGS4 is not 0 because M3 is conducting and I3 is non-zero. That means VGS3 is not 0 and VGS4 is not 0. But we're saying the current is 0 through transistor 4. That means VDS4 must be 0, which means the voltage across M4 is 0. That means the output voltage is the same as VDD because the voltage across M4 is 0. Let's look at the other condition. What happens under the other condition? If Vn is less than twice the threshold voltage, then M1 is off and M2 is on. If M2 is on and M1 is off, then we know the following. Let's look at I3. Basically, we're saying that because the current through M1 is 0, then VGS3 is 0. That means VGS is very small. If VGS3 is very small, which is the same as VGS4, then VDS4 has to be large. And that means V out has to be roughly 0 because the voltage across M4 is very large. That means you're pushing it away from VDD towards 0. So V out will be close to 0. On the other hand, if Vn is moderate, which means that it's a small swing around the DC value, then the circuit behaves as amplifier. And let's show you that as a graph. Let us plot V out versus Vn. So we have the horizontal axis, which is Vn, that's the differential input voltage, which is V1 minus V2, and the vertical axis is V out. When we plot V out versus Vn, we will have this graph. Note that if Vn is large in value, that means M1 is on and M2 is off. We're gonna have a very large voltage at the output close to VDD. And if Vn is very negative, that means M1 is off and M2 is on. That means VGS3 is very small, and for the large current going through M4 will give us a large VDS. That means V out is close to 0. Now what's interesting is in between we have this linear region. This linear region behaves as amplifier. If V1 is close to V2, that means Vn is 0 because Vn is V1 minus V2. So under the DC biasing condition, if you have a small AC signal swings at this region, V out will change linearly. So the circuit behaves as amplifier, and the higher the slope of this line, the higher the gain of the amplifier, right? Because it is delta V out over delta Vn is the gain of the differential amplifier. So the slope of this line in the linear region is basically the gain. Basically, from the large signal analysis, we're saying that if the voltage swing is too large, then the circuit will swing non-linearly between 0 and VDD. And if Vn, which is the differential voltage, is small, then the circuit will behave as amplifier and it will amplify the signal. Keep in mind that the signal clip at the bottom here close to 0 because the bottom source is biased at 0. In some applications, we would like to use two power supplies to power the circuit. For example, we can use VDD and minus VSS. Plus 5 volts and minus 5 volts can be used as power supplies. Or in some other applications can be 0 to 5 volts or 0 to 3 volts. If the circuit uses negative power supply, then the bottom clip will be at that negative value. So basically the bottom clip will be at the lowest voltage in the circuit, which is in this case is 0 volts. It can be minus VSS. It doesn't have to be 0 volts. So keep that with you, and we will use this concept when we move to the operational amplifier lecture in a few lectures down the road. Now we are interested in the small signal analysis, basically the AC gain for the single-ended differential amplifier with active load. It is the input stage for the operational amplifier, and extra modifications are added to it. We will discuss them as we continue through the course. So to develop the AC gain, we have three approaches. We will only discuss three approaches. The first approach is what we call the intuitive approach. Basically, we will come up with the gain based on our intuitive understanding of the circuit. Keep in mind that if you are a new engineer, if you are a junior engineer and you would like to enter this area, when you go to the job interviews, you prepare yourself for a career. Whether you are working in the industry, you're trying to move to the analog area, or whether you are a graduating student trying to enter into this area. And this is from my personal experience. When you go to the job interviews and people will ask you to solve for circuits, the circuits they give you, number one, are practical, number two, are difficult and challenging. So the challenging and the practical circuits are the ones that presented to you in the job interview, and usually relates to their current projects, which means they are state-of-the-art problems. So that's something you should be ready for. A lot of times you only have an hour or so to present your case, and the way you're going to solve for the circuit in the job interview is to use the intuitive approach. Intuition is important and something that acquired, gained through practice. Is not something that you study. So what we do is we're going to present some of these intuitive approaches to you as we go through the course, but as an analog engineer, you have to use your intuitive approach to design the circuit. After all, analog design is an approximated design. Actual design requires us to use simulation. So let's look at the circuit. We labeled this node X and this node Y, and let's focus on node X because node X is extremely important. The gain at node X is small because M3 is diode connected. Then we can assume that the voltage at node X does not affect the gain. This statement is very powerful. What does that mean? Well, remember that this transistor is diode connected. That means the output resistance looking into this transistor is 1 over GM3 in parallel with small RO3. But usually small RO is much larger than 1 over GM, so we neglect the small RO. We say that approximately output resistance looking into this diode is 1 over GM3, which is very small. So the gain is basically the transconductance times the output resistance, but the output resistance is very small, then AC gain is very small at node X. So at node X, the small signal is very small. We assume the AC voltage at node X is 0. This is very beautiful. Why is it beautiful? This is the trick of the circuit. If you understand this particular trick, you understood the whole concept of the active load. Let's look at this new statement. The AC current passing through M1 is the same as the AC current passing through M3. So we can say that I1 equals to I3. AC current, right? But because M3 and M4 are diode connected, because of that, then we can say that I3 equals to I4. The AC current in I3 is the same as the AC current in I4, which is nothing but GM1 times Vn over 2. This is very powerful because what it says is the AC current in M1 is transformed to M4. We used the steering concept, right? So we steered the AC current here from M1 to M4, and the AC current in M4, which is I4, is nothing but GM1 times Vn over 2. Also, the AC current of M2 is given as I2 will equal to minus GM1 times Vn over 2. So we are looking at this transistor and we're saying that the AC current in this transistor is minus GM1 times Vn over 2. Why the minus sign? Remember when we used the half circuit symmetry, we said that transistor 1 has Vn over 2 and transistor 2 has minus Vn over 2. That's why we have the minus sign here, because by half circuit symmetry, the differential voltage at M2 is minus Vn over 2. So now we can really say the output resistance at the load is given as the output resistance of M4, which is the top transistor, in parallel with the output resistance in the bottom, which is the bottom resistance, right? Because they both connected to ground. One connected to ground through the bottom and one connected to ground through VDD. So these output resistances, the top output resistance and the bottom output resistance, gonna be in parallel because they connected from the output to grounds. So we know that the top output resistance is RO4 and the bottom output resistance can be RO2. In fact, it will be RO2 in series with 1 over GM1, but RO2 is much bigger than 1 over GM1, so we're going to say RO2 at the bottom and RO4 at the top. They will be in parallel. Then we can state that RO equals to RO2 in parallel with RO4. So now I can tell you what's the output current going into the output of the amplifier. It will be the current from the top, which is I1, minus the current from the bottom, which is I2. So we can say that I out will equal to I1 minus I2. Now we can say that the AC output voltage is given by the AC output current times the AC output resistance. Then we can state that V out equals to I1 minus I2, that's basically IO, times capital RO, which is the AC output resistance. This will equal to, when you substitute for I1 and I2, we have GM1 times Vn over 2 plus GM1 times Vn over 2. The minus sign is canceling the minus of I2 term, that's why we have plus sign here. This will be multiplied by RO2 in parallel with RO4, and remember that the minus sign is cancelled with the minus of I2 term, and that makes it a plus. Now we can say that V out will equal to GM1 times Vn times the parallel resistance RO2 in parallel with RO4, and the AC gain, which is V out over Vn, is given as GM1 times the output resistance, which is RO2 in parallel with RO4. So now we have defined the AC gain intuitively. Let's go back one more time. We said that the AC current of M1 is reflected to M4 through the steering current circuit. And then we have the AC current going into M2. Then the output current, the output AC current going into the output is basically the difference I1 minus I2. And if you multiply that by the output resistance, you get the gain. And in this case was GM1 times the parallel resistance RO2 in parallel with RO4. Very intuitive way to analyze the circuit. You understood it very easily without even doing any intensive mathematics. This intuition is extremely important. Remember, carry this technique with you when you go to any job interview for analog. It shows how much you understand analog circuits. Make sure you master such techniques in analyzing and understanding analog circuits. The second approach to find the AC gain for the circuit is using the half circuit analysis. Remember that transistor 1 and transistor 2, M1 and M2, are symmetric and they have the same source, we called it VB, and say that the AC voltage at the source is assumed to be 0 if the input voltage is divided in half between the two nodes. Then what we can do is we can redraw the circuit such that the source of M1 and M2 is grounded. Keep in mind that this is for the AC circuit, so we're saying that the AC circuit has a ground source for M1 and M2. Then the circuit looks like this. But also, we know that the AC gain can be expressed as V out over Vn, which is GM-RO, whereas GM is the transconductance of the amplifier. Keep in mind that this is capital GM, that means the transconductance of the amplifier, whereas GM is basically IO over Vn. This is the AC output current over the AC input voltage, and over here I.O. is pointed to be outward, leaving the amplifier. We also know that the AC current for transistor 1, I1, will equal to GM1 times Vn over 2, where GM1 here is the transconductance of the amplifier, which is the same as I3, because the current flowing through transistor 3 is the same as the current flowing through transistor 1, but also it is mirrored to transistor 4. So basically what we are saying here is I1 equals to I3, and I3 is mirrored to I4. So I4 is the same as I1. On the other hand, we also know that AC current for transistor 2, I2, will equal to GM1 times minus Vn over 2. We use GM1 here because GM1 and GM2 are the same by symmetry, and the voltage for transistor 2 is the negative voltage minus Vn over 2. Now we would like to sum the AC current at the output. So by summing the two AC currents at the output, I.O. is equal to I1 minus I2. Basically we used KCL here, and this will equal to GM1 times Vn. But also we know the transconductance Gm of the amplifier is the AC output current over the AC input voltage, and in this case when we divide by Vn we have Gm1. So for this particular amplifier, the transconductance of the amplifier is the same as the transconductance of transistor 1. Remember, we said that the gain is nothing but Gm times Ro. So now we have to find Ro. What's Ro for the circuit? Well, to solve for Ro, we will apply Thevenin's equivalent circuit. So we will draw the AC circuit, and the AC circuit will look like this. We will have the transistors M1 and M2 connected together, and we will ground the inputs, and the current source is open circuit. So that's how M1 and M2 will look like. And then we will also have M3 and M4, and then we will apply the test voltage Vx, and we would like to measure Ix connected into the circuit. Now this circuit is very tricky, so let's look at it and see how will it behave. What I will do is, we know that when we look into M2, I will see RO2, and then I will go through M1, so I will see RO1, but I know that RO2 and RO1 are the same, so the equivalent of these two resistors is 2 times RO1, right? Because RO2 is the same as RO1 and they are connected in series. Then I will go through M3. Now M3 is very interesting. What you have is two resistors in parallel. You have RO3 in parallel with 1 over GM3. Usually we assume that 1 over GM3 is more dominant and we drop the RO3, but for now let's assume that the two resistors exist. By any means, now I would like to solve for Ix. So Ix will equal to the current going through M2, which is the same as the current going through M1, which is the same as the current going through M3, and the current going through M4. Now, the current going through M4 has two portions. One of them will go through RO4, and the other one is the current that is caused by the reflection of transistor M3, because remember, transistor M3 will also reflect the current to M4. So the current passing through M3 will reflect it to M4 under this condition. So we can say that Ix will equal to 2 times I3 plus I4. And this is a little bit confusing, but let's show you why we wrote it such a way. Because there is current will go through RO4 that is caused by Vx. Remember that is AC current, so that means the VDD is also grounded, right? From Vx, there is current will go through RO4, the output resistance through transistor 4, and there is a current will go through transistor 4 because of the current flowing through the current in transistor 3. So transistor 4 has two currents, current going through R4 and current that is reflected from M3, which is M1 and M2, right? So the current going through M3 is the same as M2 and the same as M1, and that current is reflected to M4 plus the current that is flowing through R4. You see, so that is kind of interesting. So what you will have here is Ix will equal to twice the current going through M3, because M3 will also reflect current to M4 plus the current going through RO4, so we're going to call it plus I4. So Ix equals to 2 times Ix plus I4, and this will equal to 2 times Vx over 2 times RO1 plus 1 over GM3 parallel with RO4. This is basically the current going through M1, and then you multiply it by 2, that's why we say twice times that, plus Vx over RO4. Now we're going to simplify this expression. If GM is much smaller than RO3, which is usually the case, and GM is much smaller than 2 times RO1, then we can say that Ix is approximately equals to 2 times Vx over 2 times RO1 plus Vx over RO4. And now we can find the output resistance, which is Vx over Ix, that is RO. That's the output Thevenin equivalent resistance, and that will equal to 1 over RO1 plus 1 over RO4 inverse. And let's express it as RO2 in parallel with RO4, because RO1 and RO2 are the same, so we will say that it is RO2 in parallel with RO4, which is the same conclusion we did before, that we said that output resistance looking into the output is basically the output resistance of this amplifier is the output resistance of M4 in parallel with M2. Here we have it. Now the gain is nothing but capital GM times RO, but capital GM is GM1, which is the same as GM2, and RO is the parallel output resistance of RO2 in parallel with RO4. Then the gain is given as GM1 times RO2 in parallel with RO4. The third method we will use to come up with the gain for this circuit is to use the Thevenin equivalent circuit for M1 and M2. So basically what we do is we come up to these two transistors, M1 and M2, and then from here we're going to simplify the circuit by finding the Thevenin equivalent circuit. Remember back from circuit courses that Thevenin equivalent simplify the circuit to make the analysis easier, and that is what we're doing here. Remember last lecture we have came up with the Thevenin equivalent for M1 and M2 when we discussed the differential amplifier. By using Thevenin's theorem, we can see that R equivalent for M1 and M2 is basically the sum of RO1 plus RO2, and because RO1 equals to RO2, we can say that this is equal to 2 times RO1. Remember that we did this calculation last lecture for the differential amplifier. We found the Thevenin equivalent resistance for M1 and M2, and we also calculated V Thevenin or V equivalent, and that was basically GM1 times RO1 times Vn. So now we can redraw the circuit. When we redraw the circuit, what we do is we replace M1 and M2 with V equivalent in series with R equivalent, and then we will have the top load, which is the two transistors M3 and M4. In order for us to find the gain, what we will do is we will solve for Ix1 first, which is the current flowing through our equivalent. In order for us to evaluate Ix1, we have to also look into the equivalent resistance of M3. So the equivalent resistance looking into the drain of M3 is basically 1 over GM3 in parallel with RO3, because this transistor is diode connected. So the equivalent resistance through a diode connected transistor is 1 over GM3 in parallel with RO3. Then now we can see that Ix1, which is the current flowing through R equivalent V equivalent, which is the same current flowing through M3, transistor 3, is given as V out minus GM1 times RO1 times Vin. This is basically V out minus V equivalent over the sum of the resistors, which is 2RO1, that is basically R equivalent, plus 1 over GM3 in parallel with RO3. Remember that this is the AC current, so VDDs are short circuit to ground, and everything here is an AC value. So these are the AC components. Now what we will do is we will say that 1 over GM3 is much less than RO3, then we can say that Ix1 will equal to V out minus GM1 times RO1 times Vin over 2 times RO1 plus 1 over GM3. And if we assume that 1 over GM3 is much less than 2 times RO1, then we can say that Ix1 is equal to V out minus GM1 times RO1 times Vn over 2 times RO1. So all what I did is I ended up calculating the current flowing through R equivalent, V equivalent, and M3. Now what I will do is I will sum the currents at V out, and basically we will say that Ix1 plus Im4 equals 0. That's basically by KCL. But we know that the current flowing through M4 will have two components. One of them will be a mirror image of M3. Whatever current flowing through M3 must also flow through M4. And there is another current flowing through M4 which flows through RO4, the output resistance RO4. Now we can sum the currents to be Ix1 plus V out over RO4 equals 0. Keep in mind that these two components are nothing but the current flowing through Im4. Portion of it is reflection of Ix1, the other one is the current flowing through RO4. Now we can substitute for Ix1 in this equation, so what we will have is V out minus GM1 times RO1 times Vn over RO1 plus V out over RO4 equals 0. And it's clear that we can separate the V out terms in one side and the Vn terms in one side, and then we can come up with the gain V out over Vn, and V out over Vn will equal to GM1 times RO2 in parallel with RO4. And keep in mind that RO2 and RO1 is the same, right? So this is the gain. It's the same way we have verified it using the intuitive approach, and the same way we verified it using the half circuit analysis. There is another important approach that we will not discuss here, and that approach is to use the small signal equivalent circuit. Also, the small signal equivalent circuit will include the body effect, which we neglected here. The source is not connected to ground, and you will have a body effect in the circuit that we neglected. So that's number one. And number two, it will also give you a better understanding of how VGS3 affects the overall gain, but they are very small. However, As we said, analog design is about approximations. Remember, the objective of the op-amp design as an amplifier is to design an amplifier with high gain such that when we use the feedback, we will be able to tolerate the approximation and come up with accurate gain. Okay, so the idea in analog design when you design amplifier is not to be exact as much as to be approximated, such that when you use the feedback you will come up with accurate gain. And that's the whole concept behind analog amplifier design. You make the gain so large of the op-amp such that if we use it in a feedback circuit, you have accurate gain. The idea here is to use feedback for accurate gain, but to design the transistor level op-amp or amplifier with approximation, but make sure it works. So we are done with the verification of the gain of this particular circuit. This is one of the circuits that we use in the real world inside the IC chip to design operational amplifiers or current sense amplifiers and so forth. So make sure you understand how we obtain the gain. Our last topic in this lecture is the common mode gain single-ended differential amplifier with active load. Basically, we are interested in what happens to the output voltage when the input voltage is the same in both ends. So we have a common mode input voltage to both ends, and we are interested in the output voltage. Remember, from earlier discussion, we said that the common mode gain is defined as A common mode will equal to alpha V out, which means how much the output voltage changes, over alpha V in common mode, which means how much the input common mode changes. So the ratio of the change in the output voltage over the change in the input voltage is the common mode gain. There is two conditions for evaluating the common mode gain of a differential amplifier. The first condition is to evaluate the common mode gain for perfectly matched amplifier. Under this condition, when the amplifier is perfectly matched for this circuit, for the single-ended differential amplifier with active load, we have two cases. The first case is Vout1 will equal to Vout2. This is because W over L1 equals to W over L2. That is the matched condition of the bottom transistors, and W over L3 equals to W over L4, which is the matched condition for the top transistors. The second condition is that the source of both transistors at the bottom is the same, so we can say that Vs1 equals to Vs2. That is because they are physically connected together. Because the transistors are perfectly matched amplifier, then we can combine the bottom transistors M1 and M2 into one equivalent transistor. The bottom equivalent transistor has twice the W over L ratio. It has twice the transconductance of GM1, and it also has half the output resistance RO1. We can redraw the circuit such that the two transistors M1 and M2 will have one equivalent transistor. This equivalent transistor has twice the W over L ratio, which means twice the transconductance GM1, and it will have 1/2 the output resistance RO1. Remember, RO1 and RO2 are the same because they are in parallel. That means they will have half the resistance. Now also, what we can do is we can combine M3 and M4 with their equivalent resistance. Because the voltage of the output is the same for perfectly matched amplifier. Then when we look through the drain of M3 and M4, we can replace these transistors with one equivalent resistance. This equivalent resistance will equal to 1 over GM3 in parallel with RO3 in parallel with RO4 in parallel with 1 over GM4. Basically, the equivalent resistance of M3 is 1 over GM3 in parallel with RO4, which is in parallel with the equivalent resistance of M4, which is RO4 in parallel with 1 over GM4. When you do simplify the math, and given the fact that 1 over GM3 roughly or approximately will equal to 1 over GM4, and 1 over GM3 and 1 over GM4 is much smaller than RO3 and RO4, then we can say that R equivalent is approximately will equal to 1 over 2 times GM3. Finally, remember the current source is actually a transistor that is biased to give us ISS. This transistor has an equivalent resistance, so we can say that the current source has an equivalent resistance RSS. Usually RSS is